Greetings YouTubers, welcome to part 5 in the Backcountry Water Treatment series. If you haven't seen the other videos, I always recommend you watch them in order as each one tends to build upon concepts introduced previously. In particular, part 3 begins the filter videos with a discussion of microfiltration, which is the removal of bacteria and cysts. And part 4 discusses ultrafiltration, which is the finer pore size required to remove viruses as well. Apart from just going over the filters themselves, there's substantial discussion of the microbiological threats that realistically face the backcountry traveler. This includes a look at the risk assessment of getting sick from contaminated water before and after filtration. So if you were under the impression that all filters were effectively the same in regard to their protection, or that any filter displaying the meets EPA standards logo were good enough, I strongly recommend you check out parts 3 and 4. What's new and different here is the filtration method used to achieve those now familiar log removal percentages. Micro and ultrafiltration use size exclusion to physically block microbes from passing through a filter perforated by millions of microscopic holes called pores. But there's another way to trap the contaminants in your water using electro-chemical attraction with the similar and related technologies of adsorption and ion exchange. And that's what I aim to cover in this video, so let's get to it. Water filter by adsorption is something you're probably already familiar with, even if you're not accustomed to using that particular term. And note that this spelling is not an error. Absorption is what a sponge does. It absorbs water by taking the water into itself. Adsorption is a process of adhesion, whereby tiny impurities in your water are attracted to and stick on the surface of an adsorbing filter medium. So the most commonly known adsorption media is probably activated carbon, sometimes referred to as activated charcoal. Household systems from shower head attachments and refrigerator water filters to faucet heads and pitchers typically employ activated carbon elements. In fact, you can buy it in bulk to replace the granules in your fish tank filter. So what is activated carbon and how is it different than regular charcoal? Well, charcoal, as you know, can be made in a fire. You take an organic material like wood and carbonize it with heat. A routinely suggested survival technique is to crush charcoal from your campfire in order to fashion an improvised water filter. But you never really hear anything about just how effective that might actually be. Well, in 2019, the Wilderness Medical Society convened a panel of experts on field water disinfection to evaluate the pros and cons of various treatment methods. Regarding improvisational filtration techniques using simple available products such as crushed charcoal, typically, bacteria and viruses can be reduced by as much as 50 to 85% and larger parasites by 99%. Well, that's definitely better than nothing. If I was in trouble, would I try it? Yes, I would. But for perspective on just how bad 50 to 85% is, that's less than one log removal. For bacteria, this little thing right here is over 10 million times better. So there's a massive difference between the effectiveness of these two methods. Again, see parts 3 and 4 for discussion of your risk of illness from drinking contaminated water even after varying levels of filtration. Now, charcoal filters by adsorption. Its surfaces attract contaminants out of your water and onto any available spot. As such, any given amount of charcoal's capacity to remove and collect undesirable particles is based directly on the amount of its available surfaces. So regular charcoal has a specific surface area in the range of 2 to 5 square meters per gram. 5 square meters is about 54 square feet. That's the size of a 6x9 tarp. So in a single gram of charcoal, if you were able to somehow unfold it all, there can be as much crumpled up surface area as this. But that's just for regular old lazy charcoal. What happens when you activate it? Well, basically you take a lump of charcoal and you bake it in a high heat kiln while blowing it out with either steam or chemicals. And this not only removes impurities, but it serves to open up the internal structure, creating a microporosity that dramatically increases the overall surface area. This close-up view gives you an inkling as to just how much contact surface becomes available. In fact, 1 gram of activated charcoal has a surface area in excess of 3,000 square meters, or over 32,000 square feet. That's about 1,000 times more than your average chunk of campfire charcoal. This is why granulated activated carbon is widely used in water treatment. It's highly reactive for adsorbing dissolved chemicals. So this makes it the best means to remove things like pesticides and herbicides from water sources that may have been contaminated with agricultural runoff. If you're disinfecting your water with additives like iodine or chlorine, GAC is your way to remove taste and odor left behind by those chemicals. Still, activated carbon does not kill microorganisms and is not designed for microbial removal. In fact, bacteria can actually be protected by the charcoal because it adsorbs the disinfectants that might otherwise kill them. Without unique materials or additional filtration, activated carbon won't filter most microbiological contaminants, including bacteria, viruses, cysts, coliform, and protozoa. So recalling from Part 4, Sawyer's lab report on the efficacy of their virus filter, this graphic makes the point visually. Side A is the growth medium, unperturbed by viral attack after having been cleaned with the Sawyer filter. And side B is what happens when you use a commercial charcoal filter. The little spots are where all the viruses that got by are killing their way through the background gel. So it takes special features to handle microbiological threats. That's coming, but first let's get more specific about what activated carbon does well, the removal of chemicals and heavy metals. One of the most common household applications of an activated carbon filter, at least in the States, is the ubiquitous Brita pitcher. This cutaway view of the blue filter element shows the fibrous matrix which contains the powdered activated carbon. Source water comes in from the top and trickles its way down through all the carbon and drips out through the bottom, clarified into the pitcher for drinking. So how do you know exactly how much of what was removed? Well, ANSI, the American National Standards Institute, works with the NSF to create standards for water filter performance. And Standard 42 is set for aesthetic effects. It's for things that might spoil the look, taste, and smell of your water, but aren't considered a particular health hazard. And there are two main types of contaminant removal rated under this standard, chlorine and particulates. A Class 3 taste and odor rating, for example, just means that 25% of chlorine is removed. Even a Class 1 rating only requires a 75% reduction. And for mechanical filtration, 85% efficiency meets the standard, where the classes indicate the micron size of the particles reduced. Also note, for all of the claims, there is only a pass or fail. So as far as certification to the standard goes, the NSF does do testing, but it's apparently extremely expensive. So it's common and considered acceptable to do your testing with a reputable third party that adheres to the industry standards. This data sheet for the Brita bottle is a good example of product labeling. It shows the actual percent reductions, not just the target, and gives the class rating for the size of particulates. It also identifies the third-party testing agency as the Water Quality Association. Beyond Standard 42 for aesthetic effects, there is Standard 53 for health effects. This is where you look for data on the reduction of chemicals known to have adverse health effects in sufficient concentration. This data sheet for the standard Brita filter shows what some of those numbers can look like. And while these detailed and specific numbers are exactly the kind of thing I love to see, I have to point out a problem with the idea that what you see here in any way certifies that the filter water will in fact be below the concentration levels set by the EPA. For example, the EPA sets the permissible water concentration of mercury at 2 parts per billion. The marketing claims point out that after filtration, the water's concentration of mercury is below the permissible limit. Except the filtered concentrations aren't what is being certified. All the testing really does is verify the filter's efficiency via the percent reduction. And that's fine if you're only using the NSF's target water for your influent challenge. But what if the initial concentration of mercury is higher? Then the parts per billion in your filtered water go up. An NSF certification contains no built-in guarantee that the water you drink out of the pitcher won't exceed these EPA limits. All it says is that the filter element has been measured to reduce contaminants by a particular percent. If the initial concentrations are high enough, nothing says the treated water won't exceed the established health limits. Now, that's not a criticism of either this filter's performance or the way the data is presented. For tap water systems, it probably makes sense to set reasonable parameters on the challenge water and only test to that standard. You are, after all, filtering water that's already been treated at least once by the utility company. But in the field, there's no rule governing the limit of what you might experience in your source water, so it's important to realize that all you really get from certification is a reduction amount, not a promise of water to any particular safety level. The other thing to bear in mind about claims of meeting NSF standards is there is no set list of substances that need to be reduced for certification. With the EPA's microbiological purifier standard, you have to meet the following reduction criteria. Not only does the reduction rate have to meet those numerical limits, but it has to be so for all of the threats listed. Miss your numbers for even one and you can't call your product a purifier. There is no such list for standard 53 certification. So if a manufacturer wants to claim lead reduction, the testing checks to see by how much, and the certification verifies that, and only that specific claim. A manufacturer could advertise that a filter reduces any number of toxic chemicals and choose to completely skip over the presence of lead in the water. If all the claims they do make pass testing, then a label of meets NSF Standard 53 for health effects can be added to the packaging. And that's even though the filter does nothing whatsoever to reduce the concentration of lead. Now, I just used lead here as an example. It could be any substance you might not want in your drinking water. It could be any number of substances. Again, I'm not criticizing the system. I'm just trying to point out what an NSF certification does and does not actually mean. You see, based on the way adsorption works, filter media can be, for lack of a better word, tuned to attract certain substances over others by the materials and additives used. So as such, you should never assume that all charcoal filters reduce a similar list of substances. The selection of treated impurities can be a seemingly random mix. So in choosing between filters, you might literally have to opt for lead reduction instead of copper, for instance, or vice versa. So to illustrate the point, here's a look again at Brita's standard filter datasheet. The only NSF 53 substances certified are copper, mercury, and cadmium. Now, here's page 1 of the datasheet for Brita's Long Last filter. You've got everything here from lead, mercury, and cadmium to things like asbestos, benzene, and carbon tetrachloride. So that's a lot of additional creepy stuff that the standard filter doesn't treat. But notice that copper is missing. Just because you have a better filter that reduces more types of substances does not mean it automatically covers everything that the lesser filter did. The Long Last datasheet goes on to list additional reductions under NSF 401 for emerging and incidental contaminants. And of course, it also shows the NSF 42 aesthetic effects results for chlorine and particulates. This Brita product chart visually depicts the sort of trading game you have to play between filter options. With the standard filter, you get mercury, cadmium, copper, and zinc, but you won't have any certification for lead, benzene, asbestos, or particulates. To get those missing substances, you switch to the Long Last, but then you lose copper and zinc. You also still won't have things like trichlorobenzene or select pharmaceuticals, pesticides, or herbicides. To get certification for those, you switch to the faucet filter and end up losing your mercury and cadmium. Even if you were to use a faucet filter to fill your Brita pitcher outfitted with a Long Last cartridge, you're still not getting copper or zinc. You'd have to pour your Long Last pitcher water into another pitcher with a standard filter in order to get everything shown. And as you can imagine, the relatively small number of things listed here is far from every potential drinking water threat that's known. So what's a consumer to make of all this? Is NSF 53 certification essentially meaningless? I would give you the old yes and no answer. On its own, just the assertion of meeting standard 53 is, well, kind of meaningless. You have no idea what it means. It could mean the reduction of a few relatively harmless substances, or it could mean that dozens of potentially serious contaminants are treated. You can make no valid assumption about what the protections a given filter provides simply from the claim that NSF standards have been met. Because the substances reduced could include or exclude any particular type, you have to have the data sheet to know what you're really talking about. With that list in hand, what testing to NSF standards does for you is verify the accuracy of those reduction claims. It's still, however, on you to look over that list for the substances that you may be concerned about. And without a list, there's no way to verify what you are or are not really getting. Right, so with that all in mind, let's talk about some of the backpacking options available. Platypus makes a carbon element for their Gravity Works system. It's an inline filter that connects with the standard water hoses of a bladder, gravity, or a squeeze system. It's marketed to help remove flavors and odors from water, which is the jargon of NSF 42's aesthetic effects. But under the tech specs, Platypus also says the element is effective against chemicals and toxins, sounding more like NSF 53. No claim of certification is made, however, and no datasheet is provided. I personally would expect its performance to be about that of any common activated carbon filter, essentially like a standard countertop water pitcher. Specifically, the carbon element is listed as not effective against protozoa, bacteria, or viruses, nor is it said to be effective against particulates. It's made to be used in conjunction with a microbiological filter of some kind, and the way you rig it up is to put the element in line after your primary filter. And once you've strained out the germs and the silt, the granulated activated carbon is there to pull out most of the swamp taste or bad odor that might remain. Another way to use a carbon element like this is in combination with chemical treatments such as iodine or chlorine. So my first suggestion is to switch to a chlorine dioxide based chemical. See part 2 for details on why. But failing that, an adsorption post filter can help reduce the unpleasant chemical aftertaste. Just make sure you don't carbon filter the treated water until after an ample amount of time has passed. Otherwise, you'll just be removing the active chemical ingredient before it can disinfect your drink. And the platypus here was the smallest and lightest hiking-specific carbon filter that I found. At just over an ounce, it has a stated cartridge life of about 300 liters. Another option comes from Katadyn. They sell it as a bottle adapter with activated carbon, as the design is meant to fit securely on top of popular containers like clean canteens. It's bigger and weighs closer to 2 ounces with a useful life of 200 liters. And as of this publication, you can get them on Amazon for just $2 more than the platypus. An advantage of the Katadyn model, however, is that it's refillable. They sell replacement packs, but you can get food-safe activated carbon granules in bulk for cheaper. If you plan on using carbon filtration more than just occasionally, this might be an interesting option. And so far, we've just been talking about the use of adsorption technology for the reduction of chemicals and heavy metals. Now, those are impurities at the molecular level, thousands of times smaller than some of the microbial threats you might encounter. So how well can the force of electrochemical attraction handle impurities that are 4 orders of magnitude larger in size? By analogy, consider the drain plug in your car's oil pan. It has a magnet designed to pull metal bits out of the circulating oil to prevent wear in your engine. It acts like sort of an attraction filter, cleaning the oil by plucking impurities from the passing flow. So now imagine trying to pull your car itself from a river using this same little magnet. And don't take the example too specifically, it's just an analogy, but hopefully one that illustrates the problem that scale can present to an attraction-based technology. Adsorption media can, if suitably enhanced, pull tiny viruses from your water. But bacteria are very much larger than viruses, and cysts are even larger still. Giardia can be 150% the size of this red blood cells shown in this diagram. Fortunately, by virtue of that greater size, bacteria and cysts are removable with common microfiltration. So backcountry filters that treat viruses using adsorption will typically employ some sort of traditional size exclusion filter to handle the big stuff, relying on electrochemical attraction only for the tiniest challenges. A case in point is the Sawyer S3 Select Water Purifier. It's literally a bottle with a micro squeeze filter screwed on top. The micro squeeze traps bacteria and protozoa, while a proprietary foam inside the bottle adsorbs viruses, heavy metals, chemicals, and pesticides. It's a 20-ounce container and you get up to 400 uses, making the rated life about 8,000 ounces, which is just over 62 gallons. To operate, fill the bottle with water and screw the microfilter back on. Then squeeze the water and foam together in the soft rubber bottle back and forth in an alternating motion for 10 seconds. Dispense disinfected water by squirting it through the micro squeeze filter. Now, as far as freezing goes, Sawyer says they have no proof it will harm the filter, but they also have no proof it won't, so they still recommend replacement, especially in the event of a hard freeze. Long-term storage can be wet or dry, as proprietary ingredients in the foam prevent bacterial growth and odor. And for performance, you have the 2 separate components to consider. The micro squeeze topper uses the same 0.1 micron hollow fiber membrane as the Sawyer Mini, which delivers best-in-class protozoa and bacterial removal. See part 3 on microfiltration for details, but here's another look at the lab results showing 7 log reduction for cysts and 8 log for bacteria. For the adsorption component, as discussed, performance claims are essentially meaningless without an actual list of lab-tested reduction percentages. To that end, Sawyer provides this report. Table 1 shows the results for viruses using MS2 bacteriophage as the standard proxy organism. Reduction was greater than 5 logs, which is 10 times higher than what the EPA requires. For the various molecular trespassers that might be in your water, they give you the following tables. Table 2 shows results for metals and sulfides, including stuff like arsenic, lead, and mercury. You get the influent or dirty water concentration, the effluent or filtered water concentration, and then they compute the percent reduction and list the EPA requirement. Table 3 shows the data for volatile organic compounds. These tend to be your industrial chemicals like solvents and dry cleaning fluid. I'm not sure how applicable this is to the backcountry traveler. It's good to know, but unless you're sourcing water from urban or industrial areas, these may not be threats you're likely to deal with often. Strictly from personal experience, what I do see along the trail sometimes is farmland, and where there are cows or crops, there is the possibility of runoff. That makes it nice to see these other sections within Table 3 that include the reduction values for pesticides, as well as herbicides. And we finish up with the reduction of chlorine and for a series of haloacetic acids. Now, this could be particularly useful for those of you who might be filtering after chemical treatment. Not only will this filter help remove any residual chlorine, but it can also reduce some of the undesirable byproducts that can result. See Part 2 for details, but recall that harmful haloacetic acids can form when chlorination is mixed with certain organic impurities that you'd be likely to encounter in wilderness waters. Another bottle-style purifier in this class is the Grayl GeoPress. The plastic collection cup houses the internal unit, which is composed of clean water drinking vessel fitted with a replaceable filter cartridge at the bottom. The two pieces seal against each other. You fill the cup and then press the internal bottle down into it. Water is forced up through the filter into the drinking vessel, where it's ready for you to consume directly or decant into another container for storage. The cartridge life is rated at 350 presses into a 24-ounce bottle, roughly 65 gallons. If you forget your filter on a cold night, Grayl says the cartridges are not significantly degraded from one freeze-thaw cycle, but after 3 or more, you should stop using it. Unlike the other products I found, Grayl does not appear to use a size exclusion filter in combination with their electro-adsorptive media. Like the others, they do use activated carbon to reduce chemicals, heavy metals, flavors, and odor. But instead of using a microfilter for those microbial miscreants, Grayl claims to have an ion exchange element that permanently binds pathogens from viruses and bacteria all the way up to the big cysts. And this technology allows them to meet or exceed ANSI NSF standards for both Protocol 42 and 53. And as discussed, however, a claim for NSF health effects isn't worth much without a list of the substances reduced. And Grayl doesn't have any test results on their site. So I sent them a message and asked for some. And to their credit, customer service got right back to me. And what they sent appeared to me to be a homemade spreadsheet with all the numbers seemingly coming from elsewhere. Well, being the pest that I can be, I asked them for a copy of the actual lab report. Well, I thought for sure I would never hear back from them again, but sure enough, customer service came right back with a full copy of the report from Test America Laboratories on behalf of BCS, which has handled filter testing for several other major manufacturers, including Sawyer. The report's format is detailed and very methodical, but not particularly user-friendly. They didn't calculate out the reductions as a percentage. So in order to get that, you have to find both the influent concentration and the resulting effluent for each sample, and those aren't organized together or even on the same page. So as Grayl no doubt understood, their spreadsheet's much easier to read. I cross-checked some of their numbers to verify that they were transferred properly, and everything seems to be correct. So here's the list of substances that the GeoPress is certified for, and as you can see, it's composed of volatiles and heavy metals. So while the Sawyer had a few more metals listed, the Grayl has more than twice as many volatile organics. And where there is overlap, the Grayl often has the higher reduction percentage, though not always. Sometimes Sawyer is more. What's missing from the Grayl report is mention of herbicides, pesticides, or those haloacetic acids that result from chlorination. For the microbiological threats, Grayl lists reductions of 5 log for protozoa and 6 log for both viruses and bacteria. That's EPA standard for bacteria, but 2 logs higher than required for both protozoa and viruses. The 24-ounce GeoPress weighs just over a pound, with an initial flow rate of 8 seconds per batch. And you can save some bulk and weight with the 16.9-ounce Ultra Press, though at the expense of having to make more presses, which also take a bit longer at 10 seconds each. And lastly, while he didn't have any results to share, the support rep at Grayl said they're recently certified for PFAS as well. These are polyfluoroalkyl substances used to make product coatings that resist heat and liquids. They don't break down in the environment, so they can move through soils and contaminate drinking water sources, but their health effects at low levels are uncertain. So while the reduction performance of these bottle filters is good, they tend to be some of the larger systems in this class, and despite their size and weight, they're on the lower end of effective service life as well, at around 62 to 65 gallons. Also, because of the batch format, they can be a bit tedious for the bulk processing of water. If you need to fill up a bladder for a long carry or to supply multiple people at a dry camp, it can be a lot of press and pour to get all of your containers topped up. So if you're looking for a lighter, smaller gravity-based filter that also incorporates adsorption and virus protection, Aquamira has the Red Line series. The Frontier Max is a housing for the replaceable filter element inside. It contains universal quick connect fittings at both ends and comes with accessories so you can attach a bite valve directly and drink from it. There's also an adapter for the other end so you can plug the unit into a standard hydration hose. This lets you use the Max in line with either a drink-through system or a gravity-based setup. Now, I've had this one for a while, but browsing the website it looks like Aquamira has updated the look, but it still claims the same Series 4 connectivity. At 71 grams and 120 gallons capacity, it offers virus protection for nearly twice as long as the bottle systems and at only a fraction of the weight. Though it should be pointed out that unlike the Sawyer and the Grayl with their large lists of chemical reductions, the Aquamira is only rated for NSF 42, which was the aesthetic effects standard. So that means a red line filter can only be counted on to reduce chlorine taste and odor. I suspect that that's just fine for most wilderness water, but if you're sourcing from urban or agricultural areas, you might benefit from additional chemical protection. Pathogen reduction is said to meet the EPA standards for a purifier, with cyst removal being a half log higher than required. And speaking of certificates, here it is. Though if you look at their lab results carefully, you can see that neither of the two filters tested fully met the 6 log requirement for bacteria after the first half gallon of filtration. And it's sort of a problem with the testing, not necessarily with the filter itself. The footnotes state that no species were detected in the filter effluent for the total volume analyzed, meaning 0 bacteria made it past the filter. But mathematically speaking, if your influent concentration is less than 10 to the 6th to start with, even a so-called perfect filtration can't calculate out to a 6 log reduction. Now on the virus side, the Aquamira is showing at least 5.5 log reductions, which is significantly better than the 4 logs required by the EPA. Again, for the field significance of a difference between 4 and 5 logs of reduction, see parts 3 and 4 for details and examples with accompanying risk assessment. Series 4 filter cartridges also fit in the 32-ounce Aquamira Shift bottle in case you're interested, though I'm not sure how backpacker friendly it is, being basically a double-walled insulated metal thermos. For the smallest, lightest virus filter I could find, I give you the Adventure Medical RapidPure Water Purification Straw. Well, I don't give it to you, this one's mine. I present to you the RapidPure Water Purification Straw. You pay for the small size with reduced service life, getting only 25 gallons of virus protection, but this might be an attractive option for short ultralight trips or those seeking to assemble a compact emergency kit. Adventure Medical claims the RapidPure is certified to exceed the EPA standards for a water purifier, as suggested by the cyst reduction being 1 log higher than required. They also reference a BCS lab report document, but their site has no actual links to the document and I couldn't find it with a web search. I left them a message inquiring, but unlike Grayl and Sawyer, who both answer questions quickly, I got no response from Adventure Medical. The RapidPure uses a multi-stage filter element. It uses ultra-ceram electro-adsorptive technology for the biologicals and an active carbon stage for taste and odor. And though the box says it protects against chemicals, heavy metals, and pesticides, nowhere in the documentation is there even a claim of NSF 53 for health effects, much less a list of chemicals and their reduction percentages. So if you like the filter, it's available in a variety of formats beyond just the straw version. The replaceable Purifier cartridge also fits into a housing for inline use, as well as their own Intrepid water bottle. Or you can use the universal bottle adapter to turn your favorite Nalgene into a purifier. They also offer a gravity system where a larger version of the Purifier cartridge fits into Adventure Medical's proprietary 9-liter bag, which you can just hang from a tree and let Mother Earth do the work for you. Its 125 gallons of virus protection almost doubles that of the Grayl, and this 9-liter bag system would still be lighter than carrying a GeoPress plus a spare cartridge. Though again, Grayl and Sawyer do serious toxic chemical reduction, and the RapidPure isn't documented for anything other than taste and odor. So it all depends on which hazards are of particular concern to you, given the areas where you will be sourcing water. In case you're wondering why I'm such a stickler for things like actual laboratory reports, I'll give you one example to make the point. Water2Go makes a filter bottle which they market for hiking, camping, backpacking, travel, and survival. And their website touts the extreme protection by claiming it removes up to 99.9999% of contaminants, including everything from bacteria, parasites, and viruses to pesticides, chemicals, heavy metals, and microplastics. Well, that's sort of a red flag right there, as nobody's percent removal is the same for everything. The technology is supposedly a 3-in-1 element that combines mechanical filtration with activated carbon and an electrical charge. I'm nitpicking here, but an electrical charge can't reduce the pore size, which is a physical quality of the mechanical filter. But all of these warning signs don't necessarily mean anything. Sometimes the marketing people don't accurately represent all of the very technical details that can be found in products like these. So that's why I want to see the actual lab reports, to get it from the horse's mouth, so to speak. On their testing page, Water2Go links reports from 4 different countries. They make the claim all have confirmed that the filters in the Water2Go bottles eliminate up to 99.9999% of harmful contaminants in water. Well, that means that if even one of the reports fails to confirm this percentage, then that is a factually incorrect statement. Okay, here's the report from the London School of Hygiene and Tropical Medicine at the University of London. From Table 1, summary of assay results of all samples. Not a single pathogen was removed to 99.9999%. So according to this report, not only do the filters not live up to their own website's claims, they also don't meet the standards to be considered microbiological water purifiers per the EPA. You need a minimum of 4 logs of virus protection and 6 logs for bacteria. This 3.79 log result means the filter let through more than 100 times the bacteria permitted to claim in the US that your product can purify water anywhere. So when someone makes claims of a scientific nature, it's fair to take a look at their actual scientific evidence. So there's a variety of water purifiers in this class. You've got bottles, straws, and inline options for gravity or squeeze. But how does electro-adsorption compare as a technology to the size exclusion method used by microfilters like the Sawyer Squeeze and Catadine B-Free, or ultrafiltration purifiers like the MSR Guardians? First, the pros. Adsorption can capture chemicals and heavy metals. Not even ultrafilters have small enough pores for that. You'd need a nanofiltration process like reverse osmosis to get down to the molecular level. In a related point, activated carbon will reduce taste and odor. Your Squeeze and B-Free aren't going to do much, if anything, in that regard. Next, adsorption offers virus protection in smaller, lighter options than ultrafilters, at least amongst the products currently available. Compare a Sawyer .02 or an MSR Guardian to the Adventure Medical RapidPure. Along with that follows cost. Also, since adsorption elements don't rely on extremely tiny pores the way size exclusion filters do, their flow rates can be substantially higher than ultrafilters. MSR makes a Guardian gravity system with a 10-liter bag, and they specifically brag about its fast flow rate, which they say is 2.5 times faster than the next leading gravity purifier. And that rate is 1 liter in 2 minutes, or ½ liter per minute. But the RapidPure gravity system, which uses a similarly sized 9-liter bag, features a, quote, industry-leading performance of 4.1 liters per minute. You could filter over 8 liters of water for your entire group with the RapidPure in the time it would take you to process just 1 liter of water with the Guardian. So on the pro side, you have smaller, lighter, faster, cheaper, and the unique ability to reduce chemicals, taste, and odor. Well, what are some of the cons? The first is service life. In the comparison we just looked at, that speedy RapidPure gravity system is said to be good for about 125 gallons. That's about 473 liters. The slower MSR Guardian gravity filter has a cartridge life of 3,000 plus liters, or more than 792 gallons. So part of that probably has to do with the fact that hollow fiber membrane filters can be backflushed and used some more. Adsorption filters cannot. Compare that with some of the other options discussed, like the Aquamira RED at 120 gallons, the Grayl GeoPress at 65 gallons, or the Sawyer S3 at 62, or the tiny RapidPure straw system, good for only 25 gallons. For perspective, here's a couple more virus-capable options from the Part 4 video on ultrafiltration. Lifesaver's bottle is rated at over 1,500 gallons, and the pump version of MSR's Guardian, which backflushes itself with every stroke, can handle 10,000 liters or more. That's in excess of 2,600 gallons. So that is a lot more virus protection than any adsorption filter I could find. Of course, it's without the chemical reduction. You pay a steep price in service life for that extra protection. Another, at least potential problem for the adsorption process is the possibility of electrochemical interference, or shall we say incompatibility. MSR's blog has an article on the advantages of hollow fiber membrane filters, and while they do have products to sell, their information tends to be pretty good. So I took note of this section on reliability and challenging water types. Because hollow fibers act as a sieve, physically straining out contaminants, they're effective in both clear and highly turbid water types. Their ability to stop microbes is not affected by other contaminants in the water, and variations in pH levels, salts, and temperature or color will not impede their effectiveness. And this is an important distinction from UV light, chemical treatments, or filters that rely solely on adsorption technologies. Each of these is impaired to some degree by other contaminants in the water. Of course, they make this statement without supplying any references, so another rabbit hole for me. The First Need XL Elite is a 1-pound pump filter that's been around for decades. It has a 2 quart per minute flow rate and a nominal capacity of 180 gallons. In addition to the ultrafine microstraining of larger particles, it also utilizes broad spectrum molecular capture and electrostatic removal to filter out everything from chemicals to viruses. Now, this particular format of filter may not be what you're looking for in an ultralight solution, but it's interesting for this discussion because of the way in which its adsorption technology has been tested. Most reputable filter manufacturers pay for their corporate lab reports to verify effectiveness. There's nothing shady about that, it's all very routine. Because it was one of the first filters to bring virus-level adsorption technology to the point-of-use market, the First Need has been the subject of at least 2 published scientific studies. The first is an original research piece from 2000 published in the Journal of Wilderness and Environmental Medicine. And 3 different First Need units were each tested at 7 different stages across the entire rated service life of the cartridge. And this included 2 different 48-hour stagnation periods to see what happens when the filter is left to sit with dirty water inside. And they also used 2 different kinds of challenge water, both high in turbidity. One was acidic and the other was alkaline, to see how the electrochemical attraction might be affected by varying pH levels. Turbidity and pH were both cited by MSR as factors that can impair adsorption technologies. And the results seem reassuring. Average percent removal of cryptosporidium oocysts varied insignificantly over all test conditions and remained above the EPA required 3 logs for all samples. Likewise, results for bacteria were greater than 6 log at all times. And the same was true for removal of poliovirus and rotavirus. Log removal exceeded 4 nines for every kind of water throughout the life of the filter. So there's another potential issue with a technology that uses electrochemical attraction, and that is the electrical charge of the particle in question. And viruses can vary significantly in their charge characteristics, and that net charge can vary with pH. So if you're relying solely on adsorption for virus removal, you might want to know how the filter performs against viruses with different isoelectric points. And this study from 2008, also published in the Journal of Wilderness and Environmental Medicine, took a look at the First Need's performance with this particular issue in mind. 9 different viruses were used of varying sizes and isoelectric points ranging from 4.2 all the way up to 9.0. Log reduction exceeded the EPA required for all virus types. In fact, for 2/3 of the viruses, log reduction was greater than 5, which is sort of interesting. From a low of 4.3 logs to the high of 5.43, that's greater than a 1 log difference. In other words, depending on the virus type, your filter might remove more than 10 times the amount of one than it does of the other. And then lastly, they test all 9 viruses again using pH-altered worst-case test water. In almost every case, the log reduction either increased or remained the same. In fact, there was only 1 instance of the removal actually suffering from the change. And for me, the takeaway is that if your filter is designed properly, you'll get at least the EPA minimums across a wide variety of turbidity conditions, pH levels, and isoelectric points. And can these results be applied to other types of adsorption filters? Well, we've seen that brand can matter significantly in terms of what substances are adsorbed, and to a degree by how much. Still, various adsorption technologies do share certain commonalities. So does first needs versatility mean you can also count on the Sawyer and the Grayl to handle such diversity with equal effectiveness? All I could say is hopefully. And apart from service life, another problem with adsorption filters can be their end of life. And by that I mean what's known as a failure mode. In other words, what actually happens once you've filtered all the liters of water that a given unit is capable of treating. And this ends up being the biggest potential concern with this type of removal technology. And we go back to the MSR blog for directions down our next rabbit hole. The point is made that size exclusion filters have an obvious end-of-life indicator. When they're full, they simply clog. When a filter like this has done all it can do, it just stops working. But at no point will pathogens get by and end up in your drinking water. It's like having a built-in safety mechanism. In contrast, a filter that only uses an adsorption technology has no way of indicating when it's no longer doing its job. It's then suggested that when adsorption media is overwhelmed, threats can be allowed through. And that's tricky because the water you might need to filter can vary dramatically in its dirtiness, so you never know quite how much you can filter before the media is spent. But whenever your filter does suddenly cease to remove pathogens, a pass-by technology like adsorption might silently start producing unsafe water without providing you with any warning whatsoever. This is a potentially serious, even dangerous problem. In the blog, MSR didn't provide any links or references to support their claims, so I spent quite a bit of time trying to track down the plausibility of this type of stealth failure. As it turns out, there's quite a bit of literature on adsorption systems. There are numerous such systems employed in a variety of applications, from drinking water treatment to pharmaceutical processes to cleaning up the wastewater from the textile industry, for example. As such, the issues with filter service life and maintenance are well documented and routinely managed. And I'll try to pack what I found into as compact a presentation as I can. This paper for the American Institute of Chemical Engineers contains a good description of the process, and it uses this diagram for an illustration. However, this presentation has a graphic that I think is a little more intuitive, so I'll use it while quoting the first paper. Common industrial practice is to pass the fluid to be treated through a column packed with the adsorbent. Here's a diagram of such a column, where the water goes in through the top, passes through all the adsorbent granules packed inside, and treated water exits through the bottom. Initially, all the adsorbent is clean, but as dirty water passes through, some of the available surface area begins to fill up. So because water keeps coming in from the top, that end of the adsorbent field fills up first. You begin to develop zones within the column as depicted by these shades of gray. The light gray adsorption zone, also referred to as the mass transfer zone, is the area where the impurities are actually being removed at any given time. And below that, the water is essentially already clean. So as dirty water continues to enter the filter, the adsorbent gets used up, and eventually that part of the bed reaches equilibrium with the feed and no additional net mass transfer occurs. Meaning, the adsorbent is filled and it no longer attracts anything out of the passing water. So this spent portion of the bed is represented by the dark gray zone. And as soon as the water reaches a portion that isn't completely used up, filtering resumes. As the process continues, more and more of the adsorbent reaches equilibrium with the feed, as indicated by the advancing dark color in the depictions of the column. The filter is getting used up, but it's aging gracefully so far. The outgoing water is still being reduced to near zero impurities. But the feed must travel farther and farther before encountering the portion of the bed that has not yet reached equilibrium. That means the light gray zone where adsorption occurs is effectively moving its way down the length of the filter. What happens when it finally reaches the bottom? In the adsorbency world, this is what's known as breakthrough. At this point, there's no longer enough viable filter media to trap all the passing impurities, and some of those impurities will begin to exit the filter. So this graph shows the amount of bad stuff in the water that comes out of a filter like this. Throughout the first two phases of the filter's life, the concentration of impurities is nearly zero. And once the adsorption zone reaches the bottom, however, that break point sees the concentration of stuff that gets through start to rise sharply. Or, as the engineering paper puts it in the most academic way possible, subsequently some adsorbate leaves with the column effluent, which is usually not desirable. And then lastly, the exhaustion point is when all the media is spent. Now no adsorption is occurring anymore, and the water that continues to pass through is effectively untreated. If you're still using your filter at one of these latter stages, you could be drinking unsafe water without even realizing it. Alright, well, that sounds like it could be a problem. But if you're skeptical of the concern, you might ask how so many industrial applications can still rely on adsorption processes. And the short answer is they use backup systems as fail-safes. From the presentation on sustainable sanitation comes this diagram of fixed bed adsorbers rigged in series. Untreated water flows into the first unit. The water that flows out of that unit flows directly into the second unit and on into the third before being discharged from the system. So by being connected in series, the second and third units provide redundancy. And when, not if, the first unit becomes saturated to its breakpoint and impurities start to escape, the second unit is there to adsorb them, and so on. In this way, you have a constantly connected backup for when your primary filter inevitably runs out of adsorption capacity. And from this technical sheet on activated carbon plants for the textile industry, we can see an actual redundant system at work. And they don't just rely on multiple filtration units. Breakthrough sensors like this one are used to detect when impurities begin to escape a saturated adsorption bed, so they know when to replace the failing element. Activated carbon, by the way, is used just as effectively to remove unwanted elements from air streams as it is from water flow. And just a couple of other theoretical issues to be aware of if you're going to use a filter with this type of technology. Again, with a diagram from the sustainable sanitation presentation while quoting from the chemical engineering paper, to be adsorbed, an adsorbate molecule must find its way to the adsorbent particle by convection, diffuse through the fluid film surrounding the particle, travel by diffusion along the length of a pore until it finds a vacant adsorption site, and then adsorb onto the solid surface. It's a multi-step process, and the point is that it's not instantaneous. In a filter where the water is constantly rushing by, it takes a particular amount of time to grab passing molecules from the flow and secure them to an available patch of surface. Well, this has implications for the effective flow rate on a filter's removal performance. From an adsorption modeling study published in the Journal of Chemistry, this graph shows the effective flow rate on breakthrough time. Now, obviously, filtering water twice as fast will wear out your filter quicker, but it should only do so in about half the time. And what actually happens is doubling the flow rate results in breakthrough occurring in about a quarter of the time. And the authors state, an increase in flow rate decreases the contact time of the absorbent and the adsorbate, causing reduction in adsorption capacity and service time of the bed. A reduction in adsorption capacity. Well, that means theoretically that a filter rated for 60 gallons of water might actually only treat 30 gallons before starting to leak impurities, if you push on it twice as hard as you're supposed to. And then lastly, because adsorption is a chemical process and pH affects most things chemical, the authors also looked at how the acidity of water impacts filtration performance. This related specifically to removal of lead. pH of metal solution is another important parameter that has a great impact on adsorption process. At lower pH values, adsorption capacity becomes less. Recalling in the Part 2 video on chemical disinfection, the pH of wilderness waters actually can vary significantly depending on where and when you draw from. So, what can the backcountry traveler take away from all this discussion of industrial water treatment? Saturation and breakthrough are real problems. So in order to manage such systems safely, the professionals use redundant systems as backups to provide fail-safes against eventual leakage. And they also employ specialized sensors to warn when it's time to replace exhausted units. In the field, with only one element, you have none of those precautions to save you. So to compound the situation, this type of filter has no actual end-of-life indicator. You could have no way of knowing that it's begun to fail you and that the water produced is no longer safe to drink. The only way to even guess how long you've got is with a service life estimation, but that life can vary widely based on a number of unknowns. Have I been pushing too fast? Has my water been too acidic? How do I know if I have 30 gallons left, 5 gallons, or none? Also, point-of-use adsorbent filters are generally only capable of dealing with trace amounts of contaminants. Grayl admits as much on their site. Grayl cartridges are designed to remove low levels of chemicals and heavy metals, but are not designed to protect against industrial disasters, coal ash spills, very high lead levels, mercury, nuclear disasters, high tannin concentration, or water that contains toxic blue-green algae. And they basically tell you in these conditions, find water from somewhere else. So if you're planning on using this as an apocalypse option, keep all these caveats in mind. But for the backpacker, I keyed in on the inclusion of high tannin concentration. Remember from Part 2, wilderness waters can be high in tannins as they leach out of the bark and leaves that can soak in lakes and ponds. So much so that the water can end up looking like a strong brewed tea. They might not be aesthetically pleasant, but tannins aren't considered harmful to drink. It's sort of ironic that something naturally occurring and not dangerous could overwhelm the adsorption capacity of your filter and result in harmful substances getting through. So admittedly, these are speculative concerns based on theoretical issues with adsorption technology. No manufacturer that I'm aware of provides testing data on how their filters perform at different flow rates, or how quickly they could be saturated by natural challenges like tannins or turbidity. And that's sort of the point of the concern, though. You have no idea. You have no idea how many gallons you have left, you have no idea what's actually getting through your filter, and you have no idea when that has started to happen. All you have is the manufacturer's service life estimate, and that estimate could be wrong by a power of 2 or more. So here's the best I can do for some practical specifics on how to choose a filter from this category. Most of these filters use a multi-stage element that utilizes traditional size exclusion to remove the larger pathogens like cysts and bacteria. And they only rely on adsorption for the tiny stuff like viruses and chemicals. And the Grayl is the only model that claims to rely entirely upon electro-adsorptive media for all of its filtration. And technically they refer to 2 different types: activated carbon and ion exchange. Well, adsorption and ion exchange share many common features, including design concepts, and their breakthrough curves are similar. Ion exchange resin columns are subject to the same problems of exhaustion, at which point they can also leak what they're supposed to trap. So unfortunately, that means when the cartridge does saturate, you could lose all protection instead of just some. And that's a problem if you can't tell when saturation occurs. You're relying solely on the manufacturer's guess about how long you get. To illustrate the uselessness of service life estimation, consider Grayl's approach. And they say, it's time to replace your cartridge when the press time reaches 25 seconds. But that will depend on how hard you press, and they give no indication of how hard that should be, or how you would even measure that force in the field. And as subjective as it starts out, that's unless the water is cold. And then you have no idea when to replace because no estimate for cold water press time is given. Outdoor Gear Lab provides a case in point. They did a review of the Grayl Ultralight, giving it a 15% for ease of filtration while noting it can't filter out water with any turbidity. It literally can't be pushed down. So be sure you take water from clear sources or pre-filter before use. This is an issue Grayl alludes to on their site, stating, to maximize the effective lifespan of your cartridge, always choose the clearest water available. If necessary, pre-filter the water using a handkerchief or t-shirt as you fill the outer refill. New out of the box and testing at home using kitchen sink water, the reviewer experienced an average press time of 40 seconds. But Grayl said replace it if it gets to about 25. So if the issue of an unpredictable service life coupled with an invisible failure mode that can leak pathogens into your drinking water without warning is a problem for you, then this might not be the best choice. Other filters in the class use the 2-stage approach. By using size exclusion to handle cysts and bacteria, they benefit from some of those advantages for at least part of their protection. Aquamira gives us a side-by-side comparison to show the difference. Their red filter that includes virus adsorption is rated for 120 gallons, but the same size green cartridge for cyst and bacteria protection is good for 1,000 gallons. And if you think about it, a 2-stage filter that uses elements with significantly different capacities should have 2 different service lives as well, one for viruses and another for cysts and bacteria. And to their credit, RapidPure is rather upfront about this. Right on the box, they list 2 different limits. You get 25 gallons of purification, which is the EPA term of art for virus removal, but 200 gallons of regular filtration, which is bacteria and cysts. And the included instruction sheet spells this out in plain language. After 25 gallons, the Purifier cartridge must be replaced for virus filtration to continue. As a filter, RapidPure products continue to remove bacteria and parasites, but not viruses, for 200 gallons of water. So which would you rather have, a filter that loses all protection after the first limit, or one that only loses virus protection and continues to provide bacteria and cyst reduction for 8 times longer? After all, these bacteria and cyst-only filters get thousands of hikers across the country every year with minimal problems. Although don't forget, another difference is the chemical reduction. And speaking of Sawyer, the design of their S3 systems makes it the most obvious. The orange bottle is filled with their proprietary adsorptive foam that soaks up viruses and chemicals. But for bacteria and cysts, they literally just screw a traditional hollow fiber membrane filter on top, in this case a micro squeeze. So this gets you thousands of gallons of fail-safe filtration even after the purification foam is exhausted. It even detaches so you can choose when to employ the greater protection as desired. And unlike adsorption elements, the hollow fiber filter can be backflushed for continued use. So letting go of the failure mode and service life issues, let's return to the concept of core function, which asserts that the primary trait of a water filter is not usability, but its contaminant reduction performance. And on that specific basis, the two top performers are the Sawyer S3 and the Grayl GeoPress. In addition to their virus protection, they were the only two I found that substantiated NSF 53 standards for health effects in their chemical removal. All the others seem more suited only for taste and odor reduction under NSF 42. So while Sawyer and Grayl both had impressive lists of chemicals that they reduced, the character of each filter's list is somewhat different. The Grayl tests emphasize the reduction of volatile organic compounds, which are more of an industrial type of water pollution, while the Sawyer includes reductions for pesticides and herbicides more likely to be found near ranches and farms. So your choice might be based on where you're most likely to source water from: agricultural runoff or industrial runoff. For the places I generally hike, I'm more concerned about farm chemicals than factory chemicals. I found an article from the Society for Engineering and Agriculture, Food, and Biological Systems that reported concentrations for pesticides in field runoff. The first two were specifically tested for reduction in the Sawyer's labs, including atrazine, which was found in the highest amounts. And none of these pesticides are listed in Grayl's lab report. Finally, if service life isn't a concern because you're just looking for an ultralight option for shorter trips, occasional use, or compact emergency kits, then the lightest and cheapest way to get your foot in the virus protection door is with one of these RapidPure elements. I promised that UV and solar disinfection would be next. What I'll try to do after that is develop a pros and cons chart for all the water treatment methods, from heat and chemicals to all the various types of filters. The goal is to provide you the information to make your own best option choices depending on what your priorities are: maximum protection, longevity and reliability, or things like speed and ease of use. As always, I very much appreciate your time, and thanks for watching.